May, June 2024, paper 6, variant 3. Question 1 soon determines the density of a modeling clay by two methods. In method 1, he uses the block of modeling clay shown in figure 1.1, measured the dimensions, the length, the width, and height. Okay, so measuring the dimensions, the length would be 6.2 centimeters, the width would be 3, and the height would be 2.4. So 6.2, 3, which is 3.0, and the last one is around 2.4 centimeters. If your readings are slightly less, it's okay, it's due to the printing error. Calculate the volume. Can I find the volume? Okay, length times width times height, so it's 6.2 times 3 times 2.4. So the volume would be 44.6. 44.6 centimeters cubed. Suggest why the value VA is only an approximation of the volume of the block. Describe how the accuracy VA can be improved. How can I improve this? Or first of all, why is it an approximation? Because we're not actually finding the actual dimensions. This dimension, this is actually an irregular dimension. So it's quite difficult to find this irregular dimension. How can I improve this process by repeating and taking average? So it's actually kind of difficult. Okay, to find irregular dimensions. How can I improve it? By repeating, okay, and taking average. Okay, need to repeat and take average. In C, can I find the mass MA from figure 1.2? Yes, the mass is 80.4 grams. Can I find the value of rho A, which is the density? So the density would be MA, which is 80.4, divided by VA, which was 44.6, divided by 44.6. This gives you a density of 1.8, and do not forget the unit, grams per centimeter cubed. Okay. In method 2, he uses a smaller block of modeling clay. He finds the weight using this force meter. The weight from this force meter is 0.35. So it's 0.35 newtons. The student pours the volume of water into a measuring cylinder. Record the volume V1 from figure 1.4. So from figure 1.4, the volume is 52, 54, and 56 centimeters cubed. So this is the volume, 56 centimeters cubed. Describe briefly how a measuring cylinder is read to obtain a value for the volume. How can I take the reading? You need to take the reading, okay, perpendicularly. Take the reading, okay, perpendicularly to avoid the parallax error. To avoid parallax error. You also need to take the reading from the bottom of the meniscus, right? And then he adds the modeling clay, record the new volume V2. The new volume would be 7274 centimeters cubed. And then to find the density, it would be WB times K. What was WB? Weight B. Weight B was 0.35. 0.35 times K, which is 100, divided by V2 minus V1. V2 was 74 and V1 was 56. 74 minus 56. This gives you a density of 1.9 grams per centimeter cubed. Grams per centimeter cubed. Which density, A or B, is more likely to be more accurate? In my opinion, density B is more accurate. Why? Because the volume is taken directly from the measuring cylinder. Okay, so rho B is more accurate since the volume, okay, since the volume is taken directly, okay, directly from the measuring center. Measuring cylinder. Okay. In question 2, the student is investigating how the volume of water affects the rate at which the water in a beaker cools. So I have a beaker, I have water. What is theta R, the room temperature? It is 18 degrees Celsius. It's 18 degrees Celsius. Pours a volume of 200 centimeters cubed of hot water into the beaker and records the temperature theta of the water at time 0. Okay, he records the temperature every 30 seconds. Then she pours the water out in a volume of 75 degrees Celsius, 75 centimeters cubed into the water, and repeats the measurements. Describe two precautions. What are two precautions that could be taken? First of all, take the reading perpendicularly. Take the reading again perpendicularly to avoid the parallax error, and you can leave the thermometer or wait. Okay, leave the thermometer for a while in the water before taking the reading. Before taking the reading. Basically, you need to wait until the temperature or the reading stops rising. Readings are shown in the table 2.1. Add units to the column headings. So the column headings, the time would be in seconds, temperature degrees Celsius, and temperature in degrees Celsius. Write a conclusion stating how the volume affects the rate of cooling. So when you had 200 centimeters cubed, started at 87.5 and ended at 79, which is a difference of 8.5 degrees Celsius. When you had only 75 centimeters cubed, you started at 85.5 and ended at 67, which is a difference of 18.5, if I'm not wrong. 18.5. So 85.5 minus 67, yes, it is 18.5, which is quite the difference. It is quite a huge difference. So as the volume decreases, what happens to the rate of cooling? The rate of cooling increases as the volume, okay, decreases. Okay, what happens to the rate of cooling? The rate of cooling increases. And then you need to state the numbers, or you need to write down the numbers. When you had only 200, when you had 200 centimeters cubed, the difference was 87.7. 87.5 minus 79, which is 8.5 degrees Celsius. But when you had only 75 centimeters cubed, the difference was 85.5 minus 67, which is 18.5 degrees Celsius. Using the values for the 75 centimeters cubed, can I find x1 in the first 90 seconds? Yes, in the first 90 seconds. So it was 85.5 minus 75. 85.5 minus 75 divided by the time, which is 90 seconds. This gives you a rate of cooling of 0.12 degrees Celsius per second. Then I need to repeat the experiment for 90 to 180, which is from 75 all the way to 67. From 75 to 67 divided by 90, and this is a rate of cooling of 0.089 degrees Celsius per second. Student states that it is important to start the two experiments with the water at the same initial temperature. Yes, it is. Why? Whether your values support the statement. Yes, yes, they support it. Okay. Why? Because as the initial temperature decreases, initial temperature decreases, the rate of cooling, the rate of cooling also decreases. For example, in X1, when the temperature when the temperature was equal to the initial temperature was equal to 85.5, r was equal to, or x1 was equal to 0.12. Let me write down x1 instead of r. X1 was equal to 0.12, while when the temperature, when the second temperature, or second initial temperature was equal to 75, x2, or the next, or the second rate of cooling, was equal to 0.089. Do not be mistaken, 0.12 is 0.120. The second one is 0.089, so it has decreased. Yes. Another student repeats the experiment. State two variables other than the initial water temperature that he should control. Two variables that should be controlled: the volume of the water and the room temperature. They both should be constant. In question 3, student determines the focal length of a converging lens. Describe a technique for obtaining an image that is as sharp as possible. Move the screen slowly back and forth. The shapes of the illuminated object and image are seen. Can I find HO and HI, the height of the object and the height of the image? Yes, the object would be 2.0 and the image would be 3.2 centimeters. Can I find W, which is HO divided by HI? Yes, 2 divided by 3.2 is 0.625 or 0.63 without any unit, because this is a ratio. The student repeats the procedure for 20, 30, 40, and 50. Plot a graph of U on the y-axis, U/centimeters on the y-axis, and W on the x-axis. Okay. W is unitless. For the U, 20, 30, 40, I guess we can just plot the numbers as they are. 20, 30, 40, 50, and 60. As for the W, we need to start from 0.4 all the way to 2.9. So I guess if we start from 0, which isn't a must, I know, but if you start from 0 and increase by 0.5 each time, 1.0, 1.5, 2.5, and 3.0, this would be a really good scale for this graph. Okay, let's plot the numbers. 20 and 0.4, so 20 and 0.4, where is 0.4? It's right over here. 30 and 1.0, 1.0. 40 and 1.6, 40 and 1.6, this is 1.6. 50 and 2.4, 50 and 2.4. And 62.9. Quite easy. These numbers are quite easy. Can I draw the line of best fit and then find the gradient? Yes, I can draw the line of best fit. So the line of best fit would look something like this. Yes, okay. This would be a decent line of best fit. To find the gradient, you need to use the triangle method. Okay. If you take the first number with the last number, or two very distant points on the line, do not take any too close points. So the slope would be y2 minus y1 over x2 minus x1. Okay. Yes. If we take the values, if you take the values 60 minus, let me write it down. Okay. Let me remove this line again also. So 60 minus 20 or 2.9 minus 0.4, which is a gradient of 16. Again, the gradient could be more than 16, could be less than 16. I guess I have up to 17, for example, and down to 15. The focal length is numerically equal to the gradient, so the focal length is also 16. Basically, it's a bonus mark. The student decides to continue the experiment using larger values of u. Explain why this produces less accurate values of w. So w was the w was the ratio, right? The ratio of the image to the object, or the object to the image, or whatever. If you have larger values of u, what was u? U was the distance between the object and the lens. As you increase the values of u, okay, 20, 30, 40, no, he now wants to increase these values. What would happen to the image? The image would be smaller, right? The image would be smaller. So the values of the image, the values of the height of the image would be smaller, and therefore this would be more difficult to measure, right? Values, okay, the image gets smaller, which is more difficult to measure. It gives a lot more errors, more difficult to measure. Okay, now moving on to question 4. The student investigates the relationship between the diameter of the wire and the resistance of the wire. Plan an experiment which enables her to investigate how the diameter of the wire affects the resistance of the wire. That's not too difficult. Okay, it's a very straightforward question. The diameter, does it affect the resistance or not? Yes, it does affect the resistance. We need to have several diameters for this resistance wire. How can I measure the resistance? You need to find the current and you need to find the voltage. So any additional apparatuses will be the voltmeter and the ammeter. Figure 4.1, can I complete the circuit? Yes, I can complete the circuit by drawing an ammeter in series and then a voltmeter in parallel. What should I add here? Nothing. You can just complete the circuit. Or if you want to draw a switch, it would be okay. Okay, if you want to draw a switch, it would be okay. So I have completed the figure. What is the thing that I'm changing? What is the independent variable for this question? The independent variable is the diameter of the wire. So the range of values would be the diameter of the wire. And if we're talking about diameters of the wire are usually quite small. We're talking 2 millimeters, not 2 meters, 2 millimeters. 4 millimeters, 6, okay, 8 millimeters, probably up to 10 millimeters. The wires are very thin, yes. And then, what about the controlled variables for this question? We have some very important controlled variables. Controlled, okay, variables such as the length of the wire, the material of the wire, okay, the temperature of the wire, the temperature of the wire. How can I control the temperature of the wire? By switching off the circuit between each reading. What are the missing apparatuses? We need an ammeter and a voltmeter to measure the resistance. So I've written down the missing apparatuses. Okay, the key variables. Can I write down the steps? How can I conduct this experiment? So the steps would be, okay, for each diameter, take the reading of the voltage, or you can say potential difference, V, from the voltmeter, and the reading hmm, of the current, A, not A, okay, current I, okay, from the ammeter, Then calculate the resistance R equals V over I. Repeat and take average. Repeat for example, for all of the diameters, for all of the diameters. And then, can I draw a table? Yes, I can draw a table. How can I draw the table? What are the readings that we take? First of all, what is the independent variable? Draw the table. The independent variable is the diameter in millimeters, and then the voltage or the potential difference in volts, the current in amperes, and then the resistance in ohms. For the conclusion, I can write down for every diameter, repeat the experiment and take average. Record the readings in the table. Record the readings in the table. And then how can I compare the results? Compare the results by drawing a graph. Okay, by drawing a graph or by plotting a graph of the diameter versus the resistance. Okay, that's it.